Hey, it's been too long, but I'm here to talk about something called hollow earth theory. And what that is it's not flat earth, but back in the day, people thought that potentially inside had actually been hollow cores. And I'm not talking about the kind of things that you could see in the fantasy books, but people genuinely thought this was real. In the 1600s, in fact, Edward Halley thought so, the guy that did Halley's Comet. And so for a while, some very serious British scientists thought that the Earth might be hollow on the inside. But this was disproven in the 1700s, actually, which sounds really early, because if you think about it, we didn't have any satellites then, we couldn't take any photos, we hadn't been across to all of the parts of the Earth, we couldn't do any kind of deep digging. And so the question is, how did somebody disprove that the Earth was hollow in 1775? So stop for a second and see if you can think about it. All right, welcome back. So I'm going to give you a hint. So the person that disproved it was the royal astronomer, the same royal astronomer that you found with that did the star maps. What was his face? Oh gosh, I forget it. And so what? I should probably later. So what happened was that yeah, I need to, but let me try it anyway, and then I'll probably just cut this part out. So as it turns out, we know the positions of the stars pretty accurately in 1700s, and you know approximately on what given night where the stars will be at what given time at what given place on the planet. So this means that you could have like if you had the accurate enough measurements, and if I knew what day it was and approximately what time it was, I could look up at the sky using these tools and find out where I was on the Earth using one of these star maps. And so it was kind of a pre-GPS GPS. And so you could cross-correlate all of these things. And so that means that surveyors back in the day would actually survey at night, because that's how they could draw straight lines, by using tools that would then correspond by looking at the stars where they where they are on a planet. And so one of the other devices that they used was something where they could actually get a perpendicular to perpendicular to the Earth. And so they use a plumb. Basically, what it is a huge weight that goes down, and you know that's always going to be pointing down. And because it's always pointing down, that means the other side of the straight device is always going to be pointing up. And since you know approximately what should, so then you look through it, and then you see, I know that at this time, this is what the star map should be like. And so based on what I see in the sky, I know that I'm at this location, okay? And so that's also how you can measure distance back in the day. And so at night, I could be in one city and then do that. And then the next night, I could be in another city and then do that and compare them. I can say, based on these, I know that these cities are 10 miles apart from each other. And so that's how they were drawing the Mason-Dixon line in colonial America. And so along with that, they had the surveying equipment. You may have seen these things. They have the giant wheels on them so that you know how far you're sort of walking. And so that's just clockwork. And so this stuff goes back hundreds and hundreds of years. And they have dials, and so you had odometers. So at one point, they knew that these two cities were, let's say, 10 miles apart from each other. And so they said, okay, cool, I'll come back at night, and I will put down all of the markers in between them, and I know I'm going to be walking 10 miles using my device, and I know that my device will give me a straight line. The problem is that when they got to the other city, they looked at their device, and they're like, that's weird, this wasn't 10 miles, this is a little off. I don't know why. And so the scientists in the UK at the time saw that, and they got really excited, because back in the early 1700s, Isaac Newton, when he had come up with his gravitational theory, he had proposed an intellectual exercise that said, well, suppose if this is right, then that means that mountains or large objects would also have a gravitational pull. But it would be so small that our devices probably wouldn't be able to detect them. But the Mason-Dixon line goes past a very large mountain range. And it was enough to throw off the measurements, because when you're passing a large mountain range, you're no longer pointing straight down. You're pointing down a little bit towards the mountain range. And that was enough to make drawing the Mason-Dixon line a very difficult prospect. And so it made these scientists extremely excited at that time. And so they were like, wow, this might actually work. So they went and found a mountain in Scottish territory. And they were able to measure approximately what weight, what mass that mountain would be based on its height and based on its size. I'm about to park somewhere, and then I'll finish this. And so using that, then they said, oh, well, if it's just swerving a little bit over to this side right here, then using basic math, I can find out that the mass of the Earth is about so-and-so. Now, that would either mean that if the Earth is made out of the same stuff as the mountain, more or less, then the Earth cannot be hollow, because it would have to be full of stuff in order to be of this mass. And so using that, how much this little plum deviated from the expected place, and they used the star map in order to find that out, they were able to determine approximately what the mass of the Earth was. And this was such a phenomenal experiment that the guy that did it, which was the Royal Astronomer, got the Copley Medal for it in 1785. And a much more accurate version of this was done about 20 years later by a guy named Henry Cavendish, and that's called the Cavendish experiment, which you've probably seen it before. But it was on the same principle. And so that's how scientists in the late 1700s knew whether the Earth was hollow or not. So yeah, this is a little terribly unprofessionally done version of my Comp Hist podcast, and it wasn't even Comp Hist, it's just 18th century science. Anyway, talk to you later. Bye.